In the next few videos, we'll talk about large-scale machine learning, that is, algorithms for dealing with big data sets. If you look back at the recent 5 or 10-year history of machine learning, one of the reasons that learning algorithms work so much better now than even, say, 5 years ago is just the sheer amount of data that we have now and that we can train our algorithms on. In these next few videos, we'll talk about algorithms for dealing with when we have such massive data sets. So why do we want to use such large data sets? We've already seen that one of the best ways to get a high-performance machine learning system is if you take a low-bias learning algorithm and train that on a lot of data. And so one early example that we've already seen was this example of classifying between confusable words. So for breakfast, I ate 2 TWO eggs. And we saw in this example these sorts of results where, so long as you feed the algorithm a lot of data, it seems to do very well. And so it's results like these that has led to the saying in machine learning that often is not who has the best algorithm that wins, is who has the most data. So we want to learn from large data sets, at least when we can get such large data sets. But learning with large data sets comes with its own unique problems, specifically computational problems. Let's say your training set size is m equals 100 million, and this is actually pretty realistic for many modern data sets. If you look at the US Census data set, if there are 300 million people in the US, you can easily get hundreds of millions of records. If you look at the amount of traffic that popular websites get, you easily get training sets that are much larger than hundreds of millions of examples. And let's say you want to train a linear regression model or maybe a logistic regression model, in which case this is the gradient descent rule. And if you look at what you need to do to compute the gradient, which is this term over here, then when m is 100 million, you need to carry out a summation over 100 million terms in order to compute this derivative term and to perform a single step of gradient descent. Because of the computational expense of summing over 100 million entries in order to compute just one step of gradient descent, in the next few videos we'll talk about techniques for either replacing this algorithm with something else or to find more efficient ways to compute this derivative. By the end of the sequence of videos on large-scale machine learning, you know how to fit models, linear regression, logistic regression, neural networks, and so on, even to data sets with, say, 100 million examples. Of course, before we put in the effort into training a model with 100 million examples, we should also ask ourselves, well, why not use just 1,000 examples? Maybe we can randomly pick a subset of 1,000 examples out of 100 million examples and train our algorithm on just 1,000 examples. So before investing the effort into actually developing the software needed to train these massive models, it's often good to sanity check if training on just 1,000 examples might do just as well. The way to sanity check if using a much smaller training set might do just as well, that is, if using a much smaller m equals 1,000 size training set might do just as well, is the usual method of plotting the learning curves. So if you were to plot the learning curves, and if your training objective were to look like this, that's j train theta, and if your cross-validation set objective JCV of theta were to look like this, then this looks like a high variance learning algorithm, and we would be more confident that adding extra training examples would improve performance. Whereas in contrast, if you were to plot the learning curves, if your training objective were to look like this, and if your cross-validation objective were to look like that, then this looks like the classical high bias learning algorithm. And in the latter case, if you were to plot this up to, say, m equals 1,000, right, so that's m equals 500 up to m equals 1,000, then it seems unlikely that increasing m to 100 million will do much better, and then you'd be just fine sticking to m equals 1,000 rather than investing a lot of effort to figure out how to scale up the algorithm. Of course, if you were in the situation shown by the figure on the right, then one natural thing to do would be to add extra features or add extra hidden units to your neural network and so on, so that you end up at a situation closer to that on the left, where maybe this is up to m equals 1,000, and this then gives you more confidence that trying to add infrastructure or change the algorithm to use much more than 1,000 examples, that might actually be a good use of your time. So in large-scale machine learning, we'd like to come up with computationally reasonable ways or computationally efficient ways to deal with very big data sets. In the next few videos, we'll see two main ideas. The first is called stochastic gradient descent, and the second is called MapReduce for dealing with very big data sets. And after you've learned about these methods, hopefully that will allow you to scale up your learning algorithms to big data and allow you to get much better performance on many different applications.